So let us now go back to particle in a box example, and let's try to understand what Dirac notation, how it comes about. So basically, as I have already shown here, you can see that for a particle in a box, the wave function in position space looks like this. So this is for n is equals to 1, and here the box is like this. So it goes from 0 to L. I mean, both the scenarios are possible, which is a very known fact. You can have from minus a to a or 0 to L. It doesn't matter. The physics stays the same. But the point is that you can have the wave function for different levels. So n is equals to 1 level, n is equals to 2 level, and these can be a function of space, or you can have the wave function which can be a function of momentum. So basically in momentum space, and we know that both these are related by what is called as a Fourier transformation, FT. Okay, so this is a very well known fact. Now the question lies, is it possible that we can have a representation which is independent of the which is kind of like coordinate independent representation of the wave function, irrespective of you want to see the wave function in position space or momentum space. You don't want that. You want something to be independent of these kind of space representation. This is where the Dirac notation comes about, and we can represent the state of the particle in a box by this ket vector psi n. Now interestingly, psi n is coordinate free representation. Let's write it more nicely. Coordinate free representation. Okay, now how do you move from a coordinate free representation to the representation in like momentum or position space? We can do like this. So the representation, if you want to have in position space, then what you do is you write like this. This is actually psi n of x, and if you want to have the state represented in the momentum space, then what you have is this. So this is phi. Okay, now interestingly, this particle in a box case is like, it doesn't depend on time. It's like a stationary state. But sometimes you can have quantum systems which can be represented as the wave function ket psi n, which can be a function of time. Okay, this can be a function of time because it can evolve with respect to time. Now what is the Schrodinger equation now? The Schrodinger equation now comes looks very interesting. It's like I h cross del by del t. Now d by dt acts on psi n of t, where the ket is still a function of time because it's going to evolve, is equals to h ket psi n of t. I mean, this is the case when you have cases where the state vector, the ket state vector, is dependent on time. Now let's move on a little bit. So what we understood that if you have a state, you want to represent it in the position basis, then you get the wave function psi n of x, and if you want to represent the state in momentum basis, then what you have is a wave function uh, in momentum space. So see how I'm using these two terminologies differently. I'm talking about the wave function. So more precisely, this is the wave function, and it will be much clearer as we move ahead. So what's the difference between the wave function and such kind of state? The clarity will be more as we move ahead. So this is point number one. And as you can see here in the particle in a box, we are more of dealing with uh, continuous space, right? As I have already discussed before, that the particle can move from 0 to L and the space is more of in continuous in nature. Okay, now let's come back to our discussion where we have particle in a box, but the space is discretized. Particle in a box, but the space is discrete, and mostly we had only two locations where the particle can exist, and this was the example we were looking before. So in this example, we ended our discussion with a Hamiltonian that takes the form like this: E 0 0 E. So we are not talking any hopping stuff here, which we will do it now after some time. And now here also, let me draw the diagram. So you have this case where you have 0, you have L, and you have kind of like two positions. One position exists at x1 and another position exists at x2 where the particle can be found. Now in such a case, again I can use this abstract notation of psi to represent the state of the particle. Okay, so this is a coordinate independent representation. uh, I'm not using any momentum or position basis. It's just a kind of like a cat psi, more abstract in nature. What I can do with it is that I know if I look at the whole situation in terms of position, then there are two locations where the particle can be found. Okay, and if I have a wave function, now basically now I cannot talk about a wave function, because when I talk about a function, it's more like, you can plug a lot of values of x and you get these values whose square tells you something about the amplitude of finding the particle at that location. So here basically I can talk about objects like simply psi of x1. So you plug in the value of x1, so maybe x1 is some value L by 3 for example. Then if I just plug in x1 as L by 3, then this particular thing, maybe this, if I square it, okay, this will give me the probability of finding the particle at location x1. Okay, and similarly I can have this object psi of x2, and if I say this guy is at some location maybe 2L by 3. Okay, so then the psi of x2 is equals to say 2L by 3 square will give me the probability of finding the particle at location x2. So as you can see, when I'm talking about these two objects, now I'm mostly in the position basis, or I'm in mostly talking about the coordinate representation. So in this way, if I move forward, I can have this psi cat, which is nothing but a column vector. But now when I write it in this way, psi of x1 and psi of x2, then mostly I am now writing the whole thing in a not in a coordinate independent representation, but in a coordinate dependent representation. So this kind of uh, this way of writing the state, so this is the state which is more abstract in nature, but I'm writing it mostly in the position basis. Okay, let's make it a little bit more clear. Now let's go to our particle where it is existing from 0 to L, and it exists at two places, x1 and x2. Okay, and now what I do is I say that what if the particle can be found at x1 with probability 1, and it cannot be found, or it can be found at x2 with probability 0. So basically the particle is at location uh, 1, x1. In that case, the state can be represented as 1 0, and I just name it. Let me name it as some state x1. So the state psi becomes x1 when the particle is exactly at x1, and the state psi becomes 0 1 when the particle is at position x2. Again, this is another representation, and this is a more abstract ket representation of the same thing. So these are basically states, okay, but the moment I write these numbers, then I am mostly working in the position basis. So what is this 1? So this 1 is nothing but psi of x1, which is 1, and the square is 1. Thus that is the probability of finding the particle at location x1 is high, and the probability of finding the particle at location x2 is almost 0, right? So now I think we have got an intuitive feeling of what this state notation, why it came into the picture and how it can help us. Okay, now look, let's continue with something interesting. So we remember that the Hamiltonian in such case looks like E 0 0 E. Now if I ask you what are the eigenstates of this Hamiltonian, so basically what I'm asking is what are the state, maybe there is some state, state, okay, where if I apply the H, I get the energy of that state and the state comes as it is. So let's see what kind of state can satisfy them, and these states are the eigenstates. It can be easily seen that states like 1 0 and 0 1, they satisfy the above criteria that I just talked about. So what you can see is the state 1 0 and 0 1 are also the eigenstate of the Hamiltonian that describes our system. So basically eigenstate can sometimes also serve as basis. Now why I'm talking about basis? Because these two representation of the state are the most fundamental representation of the state, and any other superposition state can be made out of this. We'll not discuss it too much, but let's move forward. Things will become clear as we move forward. But now I guess something is clear, that these psi wave functions are kind of more coordinate independent representation of the state of the particle. Now we introduced something called as state x1, which is 1 0, and state x2, which is 0 1. So we'll discuss a little bit more on this, and let's move to a particle in a box quickly. So how about we go back, and I'm going to say something that I left here. So here are something that you must know. So once you represent psi of n as a state, okay, then if you want to see how does it look in the position basis, then what you basically have is the wave function psi of x. Okay, similarly, uh, if you want psi star of x, which is the complex conjugate of psi of x, then basically this guy gets complex conjugated also. Okay, and basically the entire stuff comes from this guy. So this is the bra notation. So basically when you have the bra notation psi n, and you want to look at in position representation, then this guy is the coordinate, this guy is the complex conjugate of this guy. Okay, so now let's move forward. So similarly here, if I write x1 and if I have bra x1, this will be basically 1 0, and if I have bra x2, this will be basically 0 1 in this way, and they satisfy a very interesting uh, thing. So if you do x1 and x1, you get 1, I mean, this calculation is very straightforward. So basically you have 1 0 multiplied with 1 0 like this, and you get 1. Similarly, when you do x2 and x2, you again get 1, and this is also very simple. You get 0 1 and 0 1, you do the multiplication, you get this. So why we are talking about these objects is because when I am talking about this object and when I'm talking about this object, so you can think of this as another way. So what is the probability of finding the particle given it is at x1 and it is still at x1? So the probability we know is 1. If it is at x1, it stays in x1. So now if I ask you what is the probability of finding the particle at x2 given it is at x1, this is quite interesting, and we get 0, right? This is quite simple. So this is kind of this mathematical jargon that we have, and what we can do is that we can simplify the mathematical jargon in a very simple mathematical notation, and we can have just xi xj is equals to delta ij. This is Kronecker delta. Okay, so this is a very simple representation of this uh, product, and this kind of product is called as an inner product. This is also quite something that we have in when we talk about this Ket-Brand notation. We also deal with this inner product structure. So basically you see that the Ket-Brand notation also comes with a inner product representation. Now how does this inner product look like when you go to particle in a box? Okay, so when I'm talking about particle in a box, now particle in a box, as I am continuously saying, is more uh, of a continuous example where the object can move around between these 2 points freely. Okay, and you can have wave function psi 1 of x at level 1, and you can have wave function psi 2 of x at level 2, or you can simply represent it as psi 1 state, and you can represent it as psi 2 state. And then if I do this inner product psi 2 psi 1, then this mathematical jargon in this case, since this is more of a continuous case, looks like this: 0 to L psi 2 star x psi 1 star x dx. Okay, this is how it looks. Now basically uh, in the continuous case where you don't have metrics and all, this is how the inner product can be understood. But when you have discrete states where you are dealing with matrices and all, then the inner product is quite straightforward, and you do these multiplications of the matrices, and then you move forward. But where are we reaching at? Where are we reaching at? So in the last lecture, we were talking about, is it possible that we can make the particle hop between these two locations, which are x1 and x2. So what about the hopping? Is it possible? Well, you need to do something about the hopping, and that something is, maybe you can think of a Hamiltonian that looks like this. So if we have off diagonal terms which were initially 0, now we take non-zero off diagonal terms, then this can make the particle hop between the spaces. So and then what happens when the particle hops? So that means when you do the experiment, there is a finite probability of finding the particle at x1, and also there is a finite probability of finding the particle at x2. So this is what we call it as a superposition state. So in this case, psi can be written as, so there is a finite possibility that the object can be found in state x1, and also there is a finite possibility, or there is a probability that the object can be found at state x2. This is a superposition state. Before we didn't see this kind of objects coming in, but now because of the nature of the Hamiltonian and the nature of the stuff that we are dealing with, we have something called as a superposition state. Okay, now once we have this superposition state, let's do a little bit of more mathematical jargon. You have this as 1 0 and you have this as 0 1, and what you get at the end of the day is AB. So basically what has happened is that there is a finite probability of finding the particle at x1 and there is a finite probability of finding the particle at x2, and those probability can be calculated when you take the square mod. Like if you want to find the probability of finding the particle at position x1, how do we do this? So consider, if I want to find, if the given a quantum particle at state psi, what is the probability that I can find it in the state x1, which means that the particle is at x1. Then I do a very interesting mathematics, again the same inner product, but that looks like this. So this is a x1 and this is b x2, and this maths is quite simple. You do the inner product with this and you do the inner product with this separately. So what you get a x1 x1 and you get b x1 x2, and that is 0, and this guy becomes a, and the probability that given the object particle is in some superposition state, the probability of finding it at state x1 becomes a square, and this is how the whole maths goes on. Now this is quite simple, right? As it is very simple, you can also find what is the probability of finding it in x2, and you will simply find that this is nothing but b square, and so on. Okay, where are we reaching at? Where are we reaching at? Again, let's go back to our particle in a box, and we were dealing with two locations, x1 and x2. Okay, so instead of two locations, if I have too many locations, if I just make maybe four locations, then what becomes of this psi? Then the psi can be written as ax1 plus bx2, and there are two more spaces where you can find the particles, so cx3 plus dx4. This is a very big way of writing the whole stuff. If I have like 100 spaces where the particle can exist, looks bad. How about I change some notation? Instead of abcd, what I do is I use c1 c2 c3 and c4. Why I am doing this is because if I do this, I can write it in a more short notation, mathematically convenient, that is summation I is equals to 1 to 4 ci xi. Okay, this is what becomes of the state psi. Now if this is the case, what happens when I have n locations? How does the state look? So if I have n locations, then again the state what represents the particle looks very simple, 1 to n ci xi. What happens now when n is infinity? It's quite an interesting question. So what does we mean when n goes to infinity? When n goes to infinity, basically we have infinite number of points between these two boundaries, and when n tends to infinity, we are mostly dealing with the particle in a box case where the number of discretized points, when it goes to infinity, they are more continuous in nature. Then in such a case, this particular expression takes this interesting form, minus infinity. So the space is between 0 to L, because it becomes psi of x and x dx. Now this will give you a very beautiful understanding of what psi of x is. Now when the stuffs were discretized, when the space was discretized, these values c1 c2 c3 were telling you what is the probability of finding the particle at a particular location xi. But now when the discretized nature is kind of gone, because now you have taken so many points that it is more continuous in nature, then in such case you don't have the summation, you have the integration, and the objects which were these values which we're talking about, these if you square them, you get the probabilities of finding a particular probability of finding a particular particle at a position xi. Now when you have this continuous function, the square of this will actually tell you what is the probability of finding the particle at a particular x. Now I think now this kind of connection tells you how wave function came into the picture and how it is connected with the state. So basically when you have this Dirac notation, you write the whole thing in the Dirac notation style. The idea of wave function automatically comes as the uh, coefficients of these states where the particle in a box can exist. Now let us do a very small calculation. How about I prove to you that if I do this, which I already told before, I get this. Actually this maths can be done. It's very simple. You just need to plug in the whole stuff here and you have to continue. Let's do this. It's a very simple calculation, just for the sake of understanding. Let's do this. So what we understood, so given this abstract notation psi, and maybe let's use a more general form, let's not use particle in a box where the particle is like not bounded, then you already have this expression. And what you need to do when you are talking about this, then all you need to do is uh, this getting with this guy. Okay, now what the next step is, you get this object. Oh, basically when you do this, let's use uh, x prime, and what you have is x prime dx prime. Now interestingly, in continuous case, uh, these kind of objects are actually Dirac delta function. They are no more chronicle delta. Chronicle delta is good when you have, you know, kind of discrete xis and all, but when you are dealing with this kind of continuous stuff, then you have this Dirac delta, and we know that this is nothing but psi of x. I mean, this step is well known in quantum mechanism. If you look at the properties of Dirac delta function, this kind of integration will tell you that you get this here. So basically, I guess the notion of how the state vector looks uh, in continuous case, we started with how the state vector was introduced in continuous case where we have a particle in a box, and then we moved to discrete case where we saw how it looks in the whole matrix formalism, and then we made a connection between the discrete and the continuous case, and then we saw a quick maths here. And I think with this it is quite clear, you had a good idea about what Dirac notation is actually doing in the entire picture. We'll discuss more in the next lecture.